All right, welcome back to Easy Math with Nick. I've taken a little break for around a week or so, but now I'm back. And so today's video will be on calculus. Unfortunately, I didn't get 5 votes on that poll I posted so I couldn't let you guys decide what video I should do next. Only 2 people voted. One person voted physics. One person voted calculus. I'm just going with calculus. So there you go. Um, I made it so that I couldn't vote myself because that would skew the results. So today's topic is expressing definite integrals with sigma notation. So how we're going to tackle this is we're going to first look at this graphically and then have make an equation from that graph. So let's say we have a function f of x. Let me just do a very crude graph. X. And it's going to be something like this. Curve like that. Let me make it nicer, just for roughly quadratic. There you go. All right, and let's say we're starting at some value a. There you go. So if we want to visualize how we're going to express an integral with sigma notation, we need to think about Riemann sums. So here I'm going to visualize a Riemann sum, a left Riemann sum, with interval length, we'll say delta x. So there you go. For a let's just call this like delta x, delta x, delta x. I'm not going to give names to each of these values. I guess I could say a sub 0, a sub 1, a sub 2, whatever. A is just our starting point, all up until b, which is where we're going to finish here. So if we want to find the integral from a to b of f of x dx, in calculus class, what you do is you just visualize that all of these delta x's are going to become very, very small. So limit as delta x approaches 0. Or you have infinitely many rectangles. Limit as n approaches infinity. But so we're going to take that latter approach here. So we're going to start with limit n goes to infinity. If we're starting at 0 equals 0 to n rectangles. And so what's going to be the length of our rectangle? Well, let's see here. Our first rectangle is a minus a plus delta x. There you go. That's our x value. If we're doing, I guess if we're doing a left Riemann sum, okay, let me think about this for a second. Yeah, okay, if we're doing a left Riemann sum, so our first, if we're starting at k equals 0, what we're going to do here is we're going to have a plus k delta x. So k is equal to 0, so our height of our first rectangle is just going to be f of a. So height f of a, f of a. And our width is, well, delta x. That doesn't change. That's going to be the same. Width. I cannot spell width. I spell width with an E. That's quite embarrassing. Width, delta x. So our first rectangle is going to get us an area f of a, delta x. Now let's look at our second rectangle. Now we're going from k equals 0 to k equals 1. So we're going to have a plus 1 delta x. So a plus delta x is going to be our x value. So we're going to have a height of, there's an ant on my laptop. Sorry about that. Not really a laptop, on my computer. F of a plus delta x. And so our width, still delta x. So what's going to be our area here? Area, I should say, equals area. You know what? I'll just make this, I'll just say areas here to make this clear. our area section. F of A plus delta x times delta x. And I'll do this one more time for illustration purposes. Let's say k equals 0, k equals 1. If we go to our second iteration here, we have a plus 2 delta x. The important part here is making sure our delta x's are all equal. Without that, we wouldn't have a nice general equation that we're trying to solve for here. So we're going to have our height. Also, this is our x value right here. It's going to be a plus 2 delta x. This is where we are now. When we're at k equals 2, we're going to be right that our x value is going to be right there. A little poor arrow I drew. And so our height is going to be f. Our height of our little rectangle that we dotted out there, if we're doing Wef Riemann sum, is a plus 2 delta x. And our width is still delta x. So our area, I think you can see where I'm going with this, f plus 2 delta x, base times height. That's our height, and our width, delta x. So, all right, there you go. So as we see here, we could sort of get a general equation by looking at what we're doing here. With each k value, what's only changing is what we multiply by the delta x within the nested f function. So, well, if we look up here, I'm gonna bring this down here. Let me see if I can drag and drop. Can I do that? Nice. Look at that. Look at how cool I am. This is going to be, our general equation is going to be limit as n goes to infinity, because we're going to have infinitely many of these rectangles. F of, oops, is it letting me draw now? Okay, a plus k delta x times delta x times delta x. Now, what is delta x? I mean, if we have infinitely many rectangles, what is our delta x going to be? I mean, well, delta x here can be said to be equal b minus a over n. Because how many rectangles we have, b minus a is going to be the total length that we have here. The total length that we have here. And n is going to be the number of rectangles we have. So if we divide the total length we have here by our number of rectangles, we're going to get the number of lengths per rectangle. So that is our delta x. So that's why that's what our delta x is here, if you wanted to substitute that in, just so that makes sense. And so it sort of links to before, if you wanted to say delta x approaches 0. But the approach we're taking here, I think, is much more easy to understand. So this is going to be, let's circle this because this is important. This is our general equation for, oh wait, let me set it equal to something. Let me drag and drop it one more time. Bring it down a little bit with an arrow to show what I did up there. It's going to be equal to, integral from a to b of, that was supposed to be an f of x dx. So this is how we're going to express integral in terms with sigma notation. With the necessary limit, of course. So let's just do an example super quick. Let's say we want to express the integral from 1 to 3 of f of x dx, where f of x equals x cubed. So let's start here. What's our a? Our a equals 1. What is our that's pretty much all we need, right? What's our delta x? I mean, we're not just going to write delta x. B minus a over n. And so it's going to be 2 over n. So when we go to write this, 1 to 3 of x cubed dx is going to be, what is f of a plus k delta x? So let's get that. F of a, what's our a? 1 plus k. What's our delta x? 2 over n. So this is just equal to f of 1 plus 2k over n. And our delta x is 2 over n, so we're going to multiply that out the front when we do this here. So let me draw. Doing a lot of dragging and dropping today. bring that down. Integral, definite integral from 1 to 3 of x cubed dx is going to equal limit as n goes to infinity. K equals 0 to n of f of 1 plus 2k over n times 2 over n. Now this makes sense when we substitute in delta x for something that has n in it, because on its own, delta x really is meaningless until we give some merit to it, because on its own, what is delta x? Usually when we do like Riemann sums, we're told what we want our delta x to be. If we want all delta x's to be the same, like we obviously do here, but like we stated before, we want to do here, or if we want all our delta x's to be different for whatever reason. But that's why we have to put delta x in terms of n, so it makes sense what we're doing here. There's an ant on my computer again. Please leave. Apologize. This is very frustrating. Ant is not being nice to me. Sorry, ant. I have to kill you. There you go. Sorry about that. All right, let me make sure we've done this correctly. Yeah, I think that's correct. There you go. I'll stop it at that. I don't think another example is necessary. But note as n is approaching infinity, our delta x's are going to become very, very small, approaching 0. So this term here, limit as n goes to infinity, 2 over n, that's symbolizing that our delta x's are approaching 0. So if we were to take that other approach and say limit as delta x approaches 0, you would achieve the same result, essentially. So if you want to say that, I mean, I guess I'll do that in a different color here. You could say that equals limit as delta x approaches 0 of n k equals 0 to infinity. Oh no, that's slightly improper, but deal with it. 1 plus 2 delta x, f of 1 plus 2 delta x times delta. So this should get you the same result. But why I don't quite like this approach is you have to have the infinity at the top of the sigma notation, which begs the question, is there another way to write it? Another way to write n in terms of x, delta x? Sure there is. If we have up here delta x equals b minus a over n, bring that down here. Oh, that's kind of sloppy. Let me drag and drop once again. I'm copying it this time. I meant to copy that. I want to drag it. Give me the option to copy it. I want to copy it. Copy to clipboard. That's not exactly where I was going with this, but all right, whatever. I'll just rewrite it. If we have delta x equals b minus a over n, you can solve for n, and it's going to be n equals b minus a over delta x. So I guess we can have this at the top of the sigma instead, which is going to look quite weird, but I guess if you really wanted to, you can write this as limit as delta x approaches 0. I'm running out of room here. This is why we drag and drop again. That's becoming very useful today. Let me fix this here. It's a little longer than I want it to be, but put this down here. K equals 0. B minus a over delta x. That is quite unwieldy. F of 1 plus 2. That's just if you really wanted to write that. I'm sorry, b minus a. I thought we were doing it with general, but what's our b minus a? 2. So it's going to be 2 over delta x. My bad. Where's my eraser? There it goes. It's going to be 2 delta. B minus a equals 2. Because b is our upper limit of the integral that we start with, which is 3. A was the lower limit, which was 1. So it'd be 3 minus 1, 2. Okay. Just to restate that. So yeah, I guess this is also equal to what we had up here. But is this really useful? No, I don't think it is anyway. But if you wanted to put it like that, guess nobody's gonna stop you. So, and that makes sense conceptually as delta x approaches 0 there. The denominator is going to get smaller and smaller and smaller. And as it approaches 0, the 2 over such a small value, 2 divided by such a small value is going to approach infinity, which is why this makes sense to what we have up here. So, okay, that's just if you really wanted to have limit as delta x approaches 0 instead of n approaches as n approaches infinity as we had up there. I much prefer this approach, so use this if possible. I don't know. I would use this if possible. That's what I meant to say. I won't tell my viewers what to do. Okay, so that's the end of what I wanted to cover today. This video's on getting a little longer than I would have liked, but it's okay. So today we covered how to express definite integrals with sigma notation. Thank you for watching.